So hello everyone, this is lecture 23 for the quantum mechanics. So today's lecture is going to be quite interesting because today we will study that how can we represent any operator into the form of matrix. Okay, but before that we have to discuss something we already lagging. So that is, I gave you this, means I told you to prove these points that eigenvalues of a projection operator are 0 and 1. Sum of two projection operator is a projection operator if operators anti-commute, and the product of two projection operator is a projection operator if operators are mutually commute. So what was the meaning of that? So if A operator B operator multiplication equal to B operator A operator, then this result should be equal to this, then we will call them as commute. Okay, and if AB is minus BA, then we will call them anti-commute. So if this condition satisfied, then they should be projection vector or the operator. So let's try to prove that. First we need to prove that eigenvalue of projection operator is 0 and 1. So you know projection vectors are those vectors which satisfy these two conditions. Means that operator must be self-adjoint. Self-adjoint means it should be Hermitian. Dagger of P should be given by P. Okay, and it should be idempotent. Means square of P operator should give you P operator. So if these two conditions are satisfied, we call that operator as projection operator. Now let's find the eigenvalues of projection operator. So let's say this is the eigenstate of this projection operator and it is operating on it. It will give you lambda alpha. So this is the eigenvalue. Now let's operate P again on the both sides. So it will give you P alpha, P lambda alpha. It will give you P square alpha. And here when P will operate on the, this lambda is some scalar, it can be written in this side. P will operate again on the alpha, will give you lambda alpha. So it will be lambda square alpha. Now see this P square equal to P because this P is the projection operator. And the P alpha will give you lambda square alpha. Now this is a similar form of this. So again this lambda square should be equal to lambda. So we can write this. Now from here lambda square minus lambda equal to 0, and this can be written in this form. So lambda can be 0, lambda can be 1. That's how you can prove that the projection operator should have eigenvalues as 0 or 1. Okay. Now second was, we need to prove that sum of two projection operator is projection operator only if operators are anti-commute. So let's see. Then sum of the P1 plus P2, there are two projection operators. Sum should be projection operator, that this should be came out to be equal to this. If this equal to this, only then we can say that this is projection operator, the sum, because this P1 plus P2 gives some P, and P square should equal to P. So let's open this square. It will give you P1 square plus P2 square plus P1 P2 plus P2 P1. Now see P1 square equal to P1 because this is the projection operator and this should satisfy this condition idempotent, and P2 square will be P2. And now see, if this should be equal to this, then this whole term should be 0, only then this can be equal to this. So put this equal to 0, then here P1 P2 equal to minus P2 P1. So this is the condition of anti-commute. So if they are anti-commute, then this will be 0 and this will be equal to this, and you can call that the sum of the projection operator is projection operator again. Okay, so now let's see the this was the third point. Now we need to prove it was the sum of the two projection operator. Now we need to prove the product of two projection operator is a projection operator again. Okay, so we have the product of two projection operator P1 P2 is some P operator. So square of this should be came out to be P1 P2. So let's open this. It will be P1 P2 P1 P2. So we can write this in this form. Now let's take this P2 P1, and if the condition is they are mutually commute, so AB should be equal to BA, this first condition. So we can write P2 P1 as P1 P2. Sorry, it will be P2 P1, and this is the condition. Now P2 P1 should be equal to P1 P2. So it will be P1 P2 and P1 P1 can be written in this form. P2 P2 will be this form. So it will be P1 square P2 square. Now this P1 P2 are individually projection operators. So P1 square should be equal to P1 and P2 square should be equal to P2. So this will be P1 P2. Now this is equal to this. So we can say that the product is projection operator, and this condition is valid only when this P2 P1 equal to P1 P2 means it is commute. Okay. So that is the proof. Now I have given you these three questions also. Means you need to prove these three operators as Hermitian operator, and you already know the condition. They should satisfy this. Phi A phi should be equal to A phi phi. Now see, this phi is different from this phi. Assume here this phi dash. This is the as you know in the spherical coordinate system, this is that phi, and this phi is the eigenstate. Okay, so I represent this phi as phi dash. So everywhere you are getting this operator, this will be phi dash, and here you have the phi. So you can prove them. Let me show you the proof. So again, for the first one, we have this. So this is the operator, and let's operate. It will be phi A phi. So this is your A. This will operate on phi. So again you will take this inside, and it will be d tau is nothing but r square sin theta dr d theta d phi, and this is phi dash. Okay, we are representing this as phi dash and this is phi. So these two are different. This is the eigen state and this is your the angle of the spherical coordinate. Okay, and you know this is the volume element, so you are calculating the volume integral, so this will be equal to this. You must see my vector analysis lecture, only then you can understand this thing, that how we written this is as this r square sin theta dr theta. So now this is the easy process. Again you will just differentiate this thing, means it will be phi. You will take this d phi dash this side and this is d phi dash. Now you can integrate this thing and take this r square sin theta dr d theta outside. So this integration, use the integration by parts, this will give you this. Now this result can be written in this form, and again you will use the integration again, and this will give you this result. Now this term will be cancelled out and you will get this minus h squared square. So we already solved this kind of question, so you must know that how we are solving. We are just changing the differential to the phi star from the phi. Okay, so now this phi is separated from this partial differentiation, and it is the phi star terms. So now you can write this minus inside, so minus h squared square, and this is again the same operator a which we used inside. So I am not giving you the complete explanation because you must understand this integration. This is a simple calculations you can understand. So this is again a here, so a phi star phi, and this is the same thing, means this complete integral can be written in this form as we write it this into this form. So that time this a was the operator with this phi, now we have the a operator with the phi star, so this is equal to this. So this means that a operator is the Hermitian operator. Now again you can do the same process with the this one. So here is the solution. The second operator is this minus h squared by r square del by del r square del by del r. So you need to prove this. So operate on the phi and take this r square also. Now this r square will cancel out with this r square, and you will just use the integration by parts again with the dr. Now first you need to differentiate this r square del phi by del r with respect to r. So this is this using the product rule, this is this. Now you need to integrate separately, so this take dr with this and dr with this. So you have two integrations, and these terms are just constants, so you need to take any worry of them, just take them as it is and solve this only. So again when you use the integration by parts, now solve this integral and this integral separately. So first you will solve this will give you this result, and this will be solved here. So I solved this integral here in this right hand side, and I solved this integral here. So you don't need these proofs, okay, you just know that these operators are Hermitian. I have given you proof just for the more information. So this can be solved in this form, and you will solve this, you will get these results. Now in the last you can just take these terms together, so it will give you this. Okay, so in the last you will get only this term remaining, so this will be there, the total sum. Now see, this complete term can be written in this form, means this is, if you take this differentiation of this, then this will give you this result, means this result can be written in this form. So it will be this phi star again, and you now take you can take this phi star outside, and this is again become the operator. You can multiply r square here and r square here, so that is the same thing. So now this is your operator again, and this is with the phi star this time, and this equal to this. So you proved that this operator is also Hermitian. Now the third was this. So these calculations are easy, just they are a little bit long. So this time also you will take this operator with the phi, operate this del phi and take the differentiation with respect to theta, and use the again integration by parts, and solve them separately. So for the first one you will get this, and second one you will get this. Now again solving, some terms will cancel out, and some will become 0 after putting the limits. Okay, so that's why you will get some terms as 0. So in the last only these were remaining, these two, means these two will be remaining in the last. Now see, this can be written in this form, because if you take the del by del theta of sin theta del phi star by del theta, so when you use the product rule, this will give you this. So this complete form can be written in this form. Now again you can take this phi star outside and divide by sin theta and multiply by sin theta. It will give you d theta sin theta, and this will be again the same operator as we started, the a operator. and h cut square is always outside, so you can take that. So it will be minus h cut square sine theta, this phi star and r square, and this is a operator, it is with the phi star, so a phi equal to phi. So again we will get what was phi a phi equal to a phi phi. So well, this calculation is very easy, you can check by yourself. So if you are still having any doubt in this, you can tell me, I can put in the comment section or resolve that for you. But this is not that much important, okay? You just need to know that how we prove them. So today's lecture is started from now. So we will see that how can we represent any operator in the matrix form. So let's have a operator A having complete set of eigenstates. So we have any operator A of which we know complete basis vectors, or the eigenstates we already know all the eigenstates. Then from the completeness relation we can write this phi I equal to I. So this is the completeness relation, we already saying that. Now we can write any operator A in this form, I A I. This will give us the same result A. So write in place of I this one and this J. So see, this is I, this is J. So these are the same things. It is just this is starting from some other number, and all the states will be there, and it is starting with the I, and all the states will be there. So we are taking the same states, it's just different numbers, okay? So it can be 1 2 2 1 2 2 3 3, it can be any number, it's just the same thing, okay? Now take this one and this one inside this A, and this phi j phi I outside. So see, this will become some scalar number, so it can be written anywhere, it is just a number. So we take this left hand side, and this will be this side. So now see, this is some vector, and this is your some scalar number. So this can be represented in terms of the matrix, okay? And we write it as the Aij, and this will be phi I phi j. So we can represent for any vector in the matrix form by this Aij, okay? So this is the matrix form of that vector or the operator. So the operator A is written in the basis phi I as the sum over the outer product of the basis states, and the expansion coefficients of Aij, that are these, are given by the matrix element of A with respect to the basis states. So with respect to these basis states, we have the matrix of A. So see, this Ij can become, if it is two basis states are possible, this means 1 and 2. So Ij can go 1 1 2 2 1 2 2 1. So we will have the 4 elements in the matrix, and if it is of 3 basis vectors we have, so it will be Ij can go up to, means there will be 9 terms. So that's how you can get the 3 matrix or 4 matrix, means 3 order or the 4th order or the 2nd order matrix. That is depending on the how many basis vectors you have. So it can be written in this form, means Aij, it will be Ij with, if I and J are same, that will be A11 A22 A33 and Aij, and it is 2 1 1 2. So this can be written in this form. So now you know what is the matrix form, and we already know what is A11. So A11 is nothing but phi 1 and A. A12 is nothing but phi 1 phi 2 A. So A3 is nothing but, A31 is nothing but phi 3 phi 1 and A. So that's how you can find each and every element of the matrix of A, okay? So Aij represented by phi I A phi j. So if this is your matrix of operator A, so you can find each and every element using these formulas. So 1 1 can be given by phi 1 A and 1 2 A. So that's how you can find the matrix for any operator. Now see what you need here. To get this matrix, you need all the basis vectors. You must know all the basis vectors or the eigenstates of that operator and the eigenvalues. Means you must know what are the eigenvalues and what are the eigenstates. Only then you can write the matrix. So let's see the example. If we have the spin operator, we know this matrix. Let's assume we don't know this. Okay, we need to find this matrix. So we know the eigenstates and the eigenvalues. So eigenstates are 1 0 0 1, and eigenvalues are h cut by 2 and h minus h cut by 2, corresponding to each of them. So we represent 1 by plus and 2 by minus. So if there is some matrix, we need to find this matrix, okay? So let's assume that matrix, it is like Ax equal to lambda x. So A is operating on this first eigenstates, giving you first eigenvalue h cut by 2 and again x. So this is your eigenstate, this one. With respect to this eigenstate, we will get sz, this minus h cut by 2 sz. It is Ax2 lambda 2 x2. It is Ax1 lambda 1 x1. So that's how you can see that. So now the matrix form will be, again it is two basis vectors are possible, so it will be a11 a12 a21 22 from here. Now a11 will be phi 1 a phi 1, phi 1 a phi 2. This is the general formula. We have already proved this. Now see, when a operates with the phi 1, it will give you lambda 1 phi 1, and this a phi 2 will give you lambda 2 phi 2, a phi 1 again lambda 1 phi 1, a phi 2 will give you lambda 2 phi 2. So, and lambdas are h cut by 2 and minus h cut by 2. So first it will be h cut by 2 phi 1. So h cut by 2 will be outside phi 1 phi 1, minus h cut by 2, because a phi 2 is nothing but minus h cut by 2 phi 2, phi 1 phi 2, phi 2 phi 1 phi 2 phi 2. Now see, phi 1 phi 2 are orthogonal, so this will be 0, this will be 0, this will be 1, this will be 1. So matrix will be h cut by 2 minus h cut by 2 0 0. Take the h cut by 2 outside, it will be 1 0 0 minus 1. So see, you will get this matrix again. So that's how you can find, if the eigenstates are known and the eigenvalues are known, you can find the operator matrix. So I have given you the proof. Now try to find for the Sx and xy. So you can find that also by just knowing these eigenstates and the eigenvalues. I already told you the eigenstates and the eigenvalues for Sx and Sy. So try to find those matrix. That will be a good exercise. So let's move forward. Now try to find the matrix for the Sx and Sy. Now what is the advantage of writing these matrix? So we can solve any operation in terms of the matrix, because we know the rules followed by the matrix. So that will be easy for us. Advantage of matrix representation in quantum mechanics: when we write states and the operators as vector and matrices, then the manipulation of the objects that we need to perform in quantum mechanics can be performed in terms of the usual rules of the matrix multiplication. So because we know how to operate with the matrix and what rules are followed by the matrix, so that's why it is easy for us to do all the calculation regarding to any object. That's why we represent in terms of the matrix. Now there are some type of questions asked in the papers. So if operator is given in this form, some operator is given in this form, 0 0 1 1 0 1 1 0, so you can directly write the matrix from here. You need to write the matrix for this operator. So how you can write? So you can compare from here. These are just the coefficients, and corresponding to ij, you have the coefficients. So if you means there are 0 and 1, so there are only two eigenstates, that is 0 and 1. Let's assume 0 as the first eigenstate and 1 as the second eigenstates. So it is 1 1 2 2, and it will be 1 2 and 2 1. So corresponding to 1 1 we have coefficient as 1, corresponding to 2 2 we have coefficient as minus 1. So if 2 into 2 matrix you have, it will be 1 and minus 1 here, and it is 1 2 means first row second column it will be I, and for the 2 1 it will be minus I. So this will be your matrix. So this is the one way to find this matrix. You can directly see the coefficients and you can write the operator matrix. Otherwise you can find each and every element, like h11 you need to find. So it will be phi 1 h. So write this complete operation inside, and 0 0 outside. Operate this 0 from right inside, will be 0 0 will give you 1, and this 1 will be remaining, and 0 1 will give you 0, it will be 0, and 0 with 1 will give you 0 0, and the 0 will 0 will give you 1, and 1 0 will be remaining. Now operate from the left hand side, it will be 0 0 will be 1, and it will be 0 with this, so only 1 is remaining, so the element is 1, h11. So that's how you will get the element will be same as we did by the coefficient matrix. So h12 again you will operate with the 1 and 2, and h21 you will operate with 1 0, 2 2 you will operate with 1 1. So you will get iota and minus 1, so you will get the same elements. So that is a very easy formula. You can just see the coefficient elements and you can write the matrix. Otherwise you can always use this formula, that is for each and every element you have this formula. So now, and see, this will be always true, means this is always conjugate matrix, or a21 will be a12 star. You can see that 1 minus I, if you take the conjugate, it will be 1i. So that's how. Now if you need to you have the matrix, and it is asked that find the eigenstates or the eigenvalues for this matrix or the operator. So you know the operator, you already find the matrix for the operator. Now if you have the matrix, you can find the eigenvalues. It will be h minus lambda I. So that's how you can find the value of lambda, that will be plus minus root 2. Now corresponding to each lambda, there will be eigenvector or the eigenstates. So you already know how to find the eigenstates from the mathematical physics lectures. There I explained in detail how to find the eigenvectors. So you just take this some x vector as a1 a2, and operate this matrix ax equal to, and put root 2x. So ax equal to lambda x, and just assume x as a1 a2. So find the value of a1 a2 in terms of one another. That's how you can find the x operator or the x as the eigenstates. Same for the minus root 2, you can find the eigenstates also. So you know already how to find the eigenstates, so you can find that. So try to find them. And let's see one more question. For a spin half system, the operator corresponding to a spin angular momentum component Sz is written by. So Sz is given in this form, and see if it is given in this form, it can also be written in terms of 0 0 and 1 1. So you can represent them in any form, but it must be that you have only two eigenstates. And you can write this in form of this also. This is the up spin, this is the down spin, or the plus plus and the minus minus, 0 0 or 1 1. You can represent it in any form. All forms are the same. Now you can write this matrix directly also, as this plus plus represent 1 1 and this is 2 2. So for the plus 1 1, the coefficient is 1. For 2 2, coefficient is minus 1. So it will be 1 0 0 minus 1. That will be your Sz operator matrix. So h cut by 2 in the outside. So that's how you can write directly. And then if you have the matrix, then you can find the eigenvalues and the eigenstates. Similarly, as we find for any matrix, the eigenvalues and eigenstates, you can use the same formula. Now see for these operators also, they are raising and lowering operators. So if these operators are there, these are called the raising like plus and lowering like minus. So some operators are given, these are your operators. So you need to find the matrix for plus and minus. So see for this one, it is like plus is 1 and minus is 2. So 1 2, at 1 2 position it will be 1, coefficient 1, and others are 0. So only the 1 2 position means first row second column will be 1. So this will be your matrix for this one. So just seeing the coefficient you can write directly. And here also for S negative, it is 2 and 1. So second column or second row or first column will be 1, others will be 0. So you can write for S negative 0 0 1 0, and h cut will be outside. So just seeing this function or this operator in this form, you can directly write the matrix by seeing the coefficients. So that's how you can write these will the matrix, and you can find the eigenstates and eigenvalues now very easily. Now this is your homework. Try to solve. For spin half system, Sx is given h cut by 2 plus minus plus minus plus, and second Sy is given as h cut by 2 minus plus minus plus. Sorry, it is minus of plus minus and plus of minus plus. So you need to write the matrix for them, for these operators, and you need to find the eigenvalues and the eigenstates for all of them. So how you can do that? It is plus minus, so if assume plus as 1 and minus as 2, so it is 1 2. At 1 2 position you will have half, and at 2 1 position you will have again half, and all terms are 0. And for the Sy, it will be for the, if plus is 1 minus is 2, so 1 2 position will be minus 1 upon 2, because it is h cut by 2, and at the 2 1 position it will be plus h cut by 2. So you can write the matrix for this also. If you have the matrix, you can find the eigenstates and the eigenvalues. So today I told you how to write the how to write a matrix for any operator, and how you can find the eigenvalues and the eigenstates. So that's it for today. Thank you everyone.